The object in the middle of all of these lines, and let's start unfolding a box. Let's go to the upper right corner of this drawing and see that box beginning to unfold. And now you see all of these views kind of unfolding and coming around. And now if you go back down to the bottom, you can see how we got those views. And here are the different views, the 6 views on an orthographic projection. So that's how we got there, just looking just like that. Now let's take a look at the way they're going to ask you questions about this on the test. First of all, they're going to give you a figure like this, which happens to be figure 28, and they're going to say, okay, here's the front view of the object we're talking about here. What is the bottom view? Is it 1, 2, or 3? Well, to figure this out, you have to know a little something about how they show edges on these drawings. If you can see the edge from the way you're looking at it, for instance, if you were looking at this from the top, you could see that edge, then it would be shown as a solid line. Looking at it from the top, you could see each of these edges, and they would all be shown as solid lines. But if, on the other hand, you were looking at this from the bottom, you'd see this edge, that'd be a solid line. You could see that edge, that'd be a solid line. But these other edges, although they're still there, you wouldn't be able to see, so they would be shown, if you're looking at it from the bottom, as dotted lines. So which one of these, 1, 2, or 3, looks like the view from the bottom? Well, let's take a look at number 2. First of all, you'd see a solid line on each of the outer lines, and those would be solid lines because you could see that edge. But would you be able to see any of these other edges? And the answer is no, you would not be able to see any of those other edges, so they would all be shown as dotted lines. And so item number 2 is the view from the bottom. All of these are shown as dotted lines because you couldn't see them from the bottom. See, nothing to it. Now let's take a look at another figure. This time it's figure 30. And when you take a look at figure 30, you have an object that looks like this. It's a stair step like so. And the question is, which is the bottom view of this object? Well, once again, from above, you would see these lines, but from the bottom, you would not see those lines. So 3 is from above, but the bottom shows these lines as dashed. They're hidden lines from the bottom view. So the correct answer is drawing 1 is the bottom view of that object. Now, the most common orthographic projections are 1 view, 2 view, and 3 view. And here an example is actually a 4 view in this particular case, but the most common are 1, 2, or 3 view orthographic projections. Let's take a look at it. When a 3 view projection is used, they'll normally show you the top, front, and right side. Here's figure 32. And when you take a look at figure 32, this is a 3 view projection, and normally they'll show you the top and the front and the right side. And that's example figure 32. So I guess this would be the top. You're looking right straight down. Here's the front of it. And then here's the right side, looking at it from the right side like so. Now let's take a look at figure 27. This is what is known as an isometric projection. And that's a type of drawing which shows the object inclined at an angle to the viewer. And what that does is it lets you have kind of an overall view of what the object looks like from only one projection. On the other hand, an orthographic projection just shows you one surface, and you have to look at each surface. An isometric projection shows you a little bit more information from one projection, but yet it doesn't give you the detail to make the object. You wouldn't have enough detail to do that. So this is called an isometric projection. Now let's take a look at what this is. This happens to be a typical aileron balance weight, and on this edge of the projection, or this surface, it's actually a rounded surface. There is no edge here. It's just a rounded surface that's shown by this line like so, also shown by this kind of big broken line rather than the dashed line. And this big broken line tells you this is a rounded surface. Now we have a line going back here. This is kind of a rounded surface. And they kind of deleted the line at this point because it would interfere with your ability to see these hidden lines in here. But this is a line that goes back here like so. Now they're going to ask you, take a look at this arrow and see the direction the arrow is coming from. The question they're going to ask you is, which one of these views is the view indicated by the arrow? Well, if you're looking at the end of this, you would see this cavity in here, which is rectangular shaped, and you'd actually see the edges of it because this cavity goes clear to this edge. Here's an example on view 1. You do see the cavity and you see the edges of it. You also see hidden lines for the bolt holes going through here, and that makes sense. So here's the hidden lines for the bolt holes. But you also see this hidden line, which would presumably be an edge here. But we already explained that that is not an edge because what they did is they showed that as a rounded surface, and a rounded surface does not show as a hidden line. So it's not view number 1. View number 2 looks good, except that the cavity actually goes to the edge here, and you would see that as a solid line, not a hidden line, so that's not correct. And the correct answer is view number 3. And view number 3, you see this cavity and you see the edges of the cavity, you see the bolt holes as hidden lines, and there is no hidden line here because this is not an edge in a surrounded surface, and that is exactly the way the answer should be, and the correct answer is answer 3. So what is the name of this drawing that's inclined at an angle to the viewer? Well, this is an isometric projection. Now let's get a little less sophisticated. Let's move away from things like drawings and projections. Let's talk about something I might be able to do. Let's talk about sketches. Now what are sketches? Well, they're simple, rough hand drawings. They're made rapidly and without much detail. So a simple, rough hand drawing, that is a sketch. Now when you're doing sketching, you're really just putting some shapes together, and one or a combination of these basic shapes, a triangle or a circle or a cube or a cylinder or a cone or a sphere, one or a combination of these shapes put together will make a sketch, and that's just about all there is to it. Now, how do you do sketches? Well, I'll tell you the way you do sketches. You cheat. You use graph paper because these are hand drawings. So sketches are drawn without the use of any drafting instruments. You just do them by hand, and it makes it just a lot simpler. So the best way to make a sketch, use this graph paper and cheat. Now let's assume you have a circle, and by the way, the FA is going to ask you about this circle on the test, and that is a circle. And the question they're going to ask you is, let's assume you have a circle, let's assume it's a sketch or a drawing or even a piece of material, piece of aluminum for instance, and you want to find the center of that circle. How would you go about doing it? Well, let's assume you have a piece of aluminum here, you want to find the center of it. How would you do it? Well, what you would do first of all is draw a couple of chord lines. Now chord lines are lines that go clear across the circle and intersect the circumference of the circle at two places like we have here. And these chord lines cannot be parallel to each other. I'll tell you why in just a minute. And then what you do is take one of the chord lines and find the halfway point and draw a perpendicular line from that chord line, and that perpendicular line will go through the center of the circle somewhere. The problem is you don't know where. So one line perpendicular to a chord will not tell you the center of the circle. You have to have two of them so you can have the lines intersect. So you take the second chord line and draw a line halfway between the edges of the chord line, and it's perpendicular, and now you have a second perpendicular line, and the intersection of those two lines makes a point, and right there is the center of your circle. Notice, by the way, that these chord lines cannot be parallel to each other, because then the two lines would just lay over the top of each other. They wouldn't intersect at an angle, and it wouldn't give you the center. So if you draw two non-parallel chord lines and then draw a bisecting perpendicular from each one of them, those perpendiculars will intersect at the center of the circle. See? It's easy. But sketches are frequently drawn for use in manufacturing a replacement part, and a sketch has to, if it's used in making a part, show all the information for making it a part. Occasionally a mechanic will use the sketch to repair an aircraft, a new design, or a modification. So as a mechanic you might need to make a sketch sometimes, and they want you to know about how to do that. By the way, there is no requirement in Federal Aviation Regulation Part 91 that repairs to an aircraft skin have a detailed dimensional sketch included in the permanent records. That is not required, that it has to be included in the permanent records. Now let's assume you're about to do a repair or an alteration on an airplane, and you need to make a sketch of a part. Now the question they're going to ask you is, what are the steps you should take to make a sketch of the part? And they're going to refer you to here to figure 31. They're going to ask you, what are the steps and how would you identify these steps? Well, if you're going to make a drawing of a part, the first thing you need to do is decide how much space is this part going to take. Block in the views. And drawing 3 here is blocking in the views. That'd be your first step. Generally you say, well, the front view of it's going to take this much space, the top view will take this much space, the right-hand view will take this much space. And that's called blocking in the views, just the general views. I'm going to look at it from the front, the top, and on the right-hand side, and they'll have this general shape and take about this much space. Now the next thing you want to do is add detail. And drawing 1 up here shows you adding detail. Well, actually you're going to make a cutout here, and it's going to have a little bit more detail and a little bit more shapes. And all you're doing is adding a little bit more detail there, and that's drawing number 1. And number 4 down here has you what they call darkening the views, and that's actually cutting out the shapes. And you might darken them a little bit with a pencil in real life. And so the views are going to look like this, and that's called darkening the views, and that's number 4. And now you've got the exact shape of this object. You know exactly what it's going to look like. The only thing you don't have is dimensions. So step number 4 in this, and they've got as item number 2 is add the dimensions. So the way you draw a drawing of an object is, first of all, you block in the views, that's 3 here, and the next thing you do is add detail, that's 1 up here. The third thing you do is darken the views so that you have the exact shape of the object, and finally you add the dimensions so you now know what all the dimensions are all the way around here. And that's figure 31. Now let's take a look at another question they're going to ask you about this, and to do that let's take a look at figure 32. And here's figure 32. And they're going to say, you have done all of this. And here are the views of an object that you're working on. You're making a working sketch. And they're going to say, all right, what is the next step? Well, at this particular point, you can see that you've already blocked in the views. There's quite a bit of detail. In fact, you know the exact shape of the object. You have everything you need here. You've darkened the views. You've done everything except you don't have the dimensions. So if you looked at figure 32 and you were making this drawing, what is the next step? Well, the next step is you sketch the extension lines and the dimension lines. Now let's take a look at schematic diagrams, and this is a schematic diagram right here. By the way, the purpose of a schematic diagram is to explain the principle of operation of a system, not to show you where the parts are physically located. You're not interested in that. Another way to put it is you're trying to show the functional location of the parts, not the physical location of components. So a schematic diagram indicates the location of components with respect to each other, but not the location of the components in the aircraft itself. Now they're going to ask you, would a hydraulic system schematic diagram indicate the direction of fluid? Well, yeah, that tells you how the system works, so you would indicate that. In this particular case, you see we have these arrows. These arrows represent check valves, but they also show you the direction of the motion of the fluid in the system. So that's part of the functional location of all the parts, and that's what a schematic diagram is all about. So it tells you functional location, not physical location. So it tells you functional location, not physical location, and it's a wonderful tool for troubleshooting system malfunctions. Now, let's you and I take a look at figure 35 here. And let's answer some questions the FAA is going to ask you about the meaning of different terms. Specifically, they're going to ask you, what do all these lines mean? Well, let's see if we can figure out what all these lines mean. First of all, they're going to ask you about a hidden line. Now, this is an example of a hidden line, and it's a line that is important, but you can't see it from this view because it's covered by another piece of the part. For instance, this collar covers these lines here. You really couldn't see them. That is a hidden line. The FAA refers to a hidden line as a medium weight dashed line, also known as a hidden line, and it's a type of line normally used in a mechanical drawing like this or a blueprint to represent an edge or an object that would be not visible to the viewer. They call it a series of short dashes evenly spaced. So that's a series of short dashes evenly spaced. That's what it looks like to me, and that is called a hidden line. They will also ask you about an extension line. What is an extension line? Well, it's a light, solid line like this one right here that extends from the point of the view to which a dimension refers. So this part right here, we want to know the dimension to that part or piece right there. So you have this extension line. You can come up here and read that dimension, and the dimension is 0.25, and this is called an extension line. Still on figure 35, they're going to say which one of these lines is an extension line. We've already pointed it out. Line 3 here is an extension line, and it tells you it's a line you use as a reference for measurements. Now let's take a look at figure 34, and we'll take a look at some other questions they're going to ask you. They're going to ask you, what are dimensions? Well, there are dimensions all over this chart. Dimensions are the means of conveying measurements through the medium of drawing. So here you convey measurements with dimensions right there. Now, if you were driving your car and you wanted to find a particular location, you'd probably get out a map and look at it. And if you wanted to find a particular spot on a map, you'd use these letters across the top, these numbers on the left-hand side, and you might find it's B2, and that would tell you it's in this square right here. It's a very handy way of locating things on a map. Well, you can do the same thing on aircraft blueprints. And these are called zone numbers. When you find them on aircraft blueprints, they tell you where to look for parts and sections and views on large drawings. And they're called zone numbers. They're very handy. Now let's take a look at figure 33, and when you get to figure 33, what you see is the symbols for different kinds of materials. And these are called section line symbols. They're going to ask you which one of these on figure 33 represents cast iron. This is the section line symbol for cast iron. It's number 3. And if you are making a drawing, for instance, a working drawing for an individual part, normally the kind of material that would be used is going to be specified on a note somewhere or on a parts list. So therefore, it's not necessary to repeat the information by using a specific section line symbol. And if you just want to use a symbol that says, look elsewhere for the material, this is just showing you that there is material, what you do is use a symbol for cast iron. And once again, in this case, figure number 3 or drawing 3 is the section line symbol for cast iron. Now let's assume you're looking at a chart like the one on figure 36 and you'd like to know some measurement off that chart for some item here. Well, the way to do it is to read the dimension off the chart, and if you need to figure out some distance, calculate it, but don't use a scale and measure or scale off the aircraft print, because the paper shrinks or stretches when it's made, and if you just try and scale off of it, it will not be accurate. So measure or calculate dimensions, don't try and scale them off the drawing. Okay, taking again a look at figure 36, the question is, what is the diameter of the holes in a finished object? So here are the holes. This note tells us how to figure out the diameter of the holes, and it says drill using a 31/64" drill and then ream to 1/2 inch. Now the question is, which is more precise, drilling or reaming? Well, the answer is you first drill the hole, and to get a precise measurement, you ream it, and they're saying in this case ream it to 1/2 inch. So the answer is 1/2 inch. So if anyone has ever given you a ream job and really reamed you out, you know that you've had precision treatment, because reaming is very precise. That's the final dimension. Now let's take a look at figure 34, and you and I will take a look at a drawing of a clevis. Here's the front view. You'll drop a bolt through here. Here's the top view like so, and the bolt will take shear loads, and that's called a clevis bolt. You'll drop through this clevis, and you're going to drill a hole in this clevis. Now the question they're going to ask you on the test is, using the information given in this drawing, what drill size would be required to drill this clevis bolt hole? Well, they tell you the bolt hole is 0.3125. So the question is, when you're talking in fractions of an inch, which drill size will that be? All you have to do is take a look at the answers they're going to make available to you. They'll make 3 of them, and they'll make available to you 21/64. Well, you can figure that out by taking your calculator and taking 21 divided by 64. 5 divided by 16 would be another answer, and another answer is 9 by 32. Do that division with each one of these, and one of them will come out to 0.3125, and the answer in this particular case is 5/16 of an inch is 0.3125, and that's the whole purpose of that question. Now, staying right here on figure 34, they're going to ask what would be the minimum diameter of 4130 round stock. You're going to use round stock to make this clevis. Now, if you look over here, you're looking for a final dimension here of 7/8 of an inch. Now, you're going to machine this down to get it down to 7/8 of an inch. So what size do you have to start with to begin with? Well, the answer is you have to start with something bigger than 7/8 of an inch. Let's take a look at the answers. First of all, answer A is 55/64. Well, 7/8 of an inch, 8 times 7 is 56/64. So this is smaller than 7/8 of an inch. You couldn't use that. You want something bigger than 7/8 of an inch, so answer C is not correct, because you want to machine it down to 7/8 of an inch. The only possible answer is 1 inch. So if you started with 1 inch stock, you could then machine it down to 7/8 of an inch, and that's all there is to it. Now let's take a look in the upper left-hand corner of figure 34, and I want to show you very close to a trick question with a very easy answer when you know the answer. And the question they're going to ask you is, take a look at figure 34, and what is the dimension of the chamfer? C-H-A-M-F-E-R, chamfer. And the answer is, what in Sam Hill is a chamfer? Well, a chamfer is a beveled edge or corner of an object, and the dimensions of this chamfer, and once you know that, you've got it made, because all you have to do is read the dimensions off this drawing. The dimensions are 1/16 of an inch times 45 degrees. They make it just a little bit more complicated than that. They ask you in decimals rather than fractions. So what are the dimensions of this chamfer? Well, divide 1 by 16, you get 0.0625, and it's still times 45 degrees, and those are the dimensions of the chamfer, and that's all there is to it. Now let's take a look at figure 37, and here's a case where you would like to just simply scale something off the chart, because they ask you what is the vertical distance between the top of the plate up here and the bottom of the lowest hole. and the lowest, and it's the lowest 15/64 hole. There's a hole down here, but the holes we're talking about are the ones that measure 15/64. There's 1, 2, 3, 4 of these. So we're asking for this distance from up here down to the bottom of that hole. Well, it's just a pencil and paper trick. All you have to do is find each of these dimensions and add them up. Let's start at the top. From the top of the hole, or top of the plate down to the middle of the top hole is 3/8 of an inch. You need an electronic calculator and figure out what that is if you don't know off the top of your head, but it's 0.375. So the first dimension we're going to write down there is 0.375. And then we're going to go from the center of the first hole to the center of the second hole. So that's this distance right here. That's 7/8 of an inch. So all we have to do is put that down with our calculator, and that's 0.875. We'll total that up. And then we're going to go from the center of the second hole to the center of the third hole. And let's see what that is. That's another 7/8 of an inch. So once again, that's 0.875. And then we're going to go from, in this particular case, from the center of the third hole to the center of the fourth hole, and that distance is different. It's 1/8 of an inch. It's shown right here. It's this distance right here, shown right down there, and we've taken the calculator at 0.125. Now we've gotten down to the center of the fourth hole, but we're trying to go to the bottom of that hole. We know that each of these holes, it says off this drawing, are 15/64. Half of that would be 15/128. So all we have to do is take our calculator to find half that distance, the last part from the center of the hole to the bottom of the hole. 15 divided by 28, and you get 0.117. Add these up, and you get 2.367, and that is the correct answer, and that is all there is to it. Now, you notice sometimes when you're reading a drawing, they will give you a range of permissible dimensions of a part. In this particular case, they said the part was 0.221 plus or minus 0.003. And if you take the minus 0.003 and add it to the plus 0.003, that is the tolerance, because tolerance is the difference between the extreme permissible dimensions of a part, and you get a tolerance here of 0.006. On the other hand, there is another concept called allowance, and that's the difference between the nominal dimension of the part and either its upper or lower limit. So you have an allowance 0.003 in either direction in this particular case. So that concept is the concept of allowance. Tolerance is the total, allowance is the one in each direction. Now here's a question they're going to ask you. What is the allowable manufacturing tolerance for a bushing where the outside dimensions shown on the blueprint are like this? It's 1.0625 plus 0.0025 minus 0.0003. Now, what is the tolerance? Well, the tolerance is the sum of the 0.0025 and the minus 0.0003. If you add those together, say you're going to each direction, it's 0.0028, and that is the tolerance. You guys have got it. Let's do another one. This time, let's assume you're reading a blueprint, and the dimension is given as 4.387 inches plus 0.005 and minus 0.002. What's the maximum acceptable size of that part, and what's the minimum acceptable size? This is very easy arithmetic. The maximum acceptable size goes like this: 4.387 plus 0.005. Add them together and you get 4.392. And the minimum acceptable size is 4.387. That's the nominal size minus 0.002, and you get 4.385, and that's all there is to it. Now let's go back to figure 34 and look at that clevis hole one more time. And the question is, what is the maximum diameter of the hole for the clevis pin? Well, here's the hole. It's 0.3125 plus 0.005 minus 0.000. They don't allow anything minus. Obviously, the pin has to fit in there. It could be a little bit bigger, but you can't make it any smaller. The pin won't fit. So what is the maximum diameter allowable? Well, all you have to do is add this up. 0.3125 plus 0.005, and you get 0.3175, and you can see your electronic calculator is going to become very, very handy when you're doing this. Well, believe it or not, you and I have covered everything the FAA wants you to know about aircraft drawing.
Let's talk now about aircraft aircraft materials and processes. And one of the processes we're going to talk about, the first one we're going to talk about, is welding. And here is some pretty good welding going on, but we're going to talk about the characteristics of a good weld, and we're going to take a look at some figures in the book and talk about what a bad weld looks like and what particular welds indicate as far as why it's bad. Okay, one of the characteristics that you should know about of a good gas weld is that it tapers off smoothly, like this good weld does, into the base metal. This has got a nice good horseshoe shape to it, and it tapers off very smoothly into the base metal. Now, another characteristic of a good weld is that no oxide should be formed on the base metal more than a ½ inch from the weld itself. No oxide should form on the base metal more than a ½ inch from the weld itself if you've got a good weld. Now, let's assume you've got a weld with a crack. If you've got cracking like this, that's obviously not a good weld. And what it means is that a part has cooled too quickly after being welded. That cracking comes because the part has cooled too quickly after being welded. Now, as a mechanic, what in general do you look at when you're examining and evaluating a welded joint in an aircraft part? Well, first of all, you want to start with the big picture. And to do that, you should be familiar with the joined parts, the proportions of the weld depth to the material thickness, and the formation of the weld. And of course, in your examination, you'd want to check some details. Details such as uniformity in the width of the weld, the penetration of the weld, the presence of any gas pockets or irregular or pitted edges, and cracks that are adjacent to the weld. Now, the FAA might ask you, should you be familiar with the likely ambient exposure conditions and intended use, type of weld, and original part composition when you are examining and evaluating a welded joint? Well, that's nice to know information, but it's really the responsibility of the manufacturer or of the repair shop that makes the weld. Or the FAA might ask you, should you be familiar with the welding technique, the filler material, and the welding temperature range? And again, that kind of information is important for the manufacturer or the repair shop making the weld. But as the mechanic who's going to install or inspect the welded part in an aircraft, you should be familiar with the parts, the proportions, and the formation of the weld. Now take a look in the FAA figure pages at figure 44, which gives examples of 4 different types of welds. The FAA will give you this and ask you which one of these illustrations, 1, 2, 3, or 4, illustrates a cold weld. A cold weld is illustrated in number 2 in the upper right-hand corner here. With a cold weld, the weld will appear rough and irregular, and with the edges not feathered into the base metal. That's indicative of a cold weld in illustration 2. And by the way, if you're looking at this and scratching your head and saying, boy, I sure hope that the FAA picture quality on the test is better than this, it's not going to be. So if you have trouble seeing the detail on these welds, you may just have to memorize which one represents what kind of weld. The FAA may ask you, for instance, which of these welds would be caused by an excessive amount of acetylene. Take a look in the lower left-hand corner at illustration number 3. That weld would be caused by an excessive amount of acetylene because what you've got here is slight bumps along the center and craters at the finish of the weld. Those are caused by the boiling of the puddle, and that's caused by excessive acetylene being used. Now let's assume that you have a really ugly weld. a really ugly weld, like for instance this one. You've got holes and some projecting globules in that weld. What do you want to do about it? What you want to do is you want to remove all of the old weld, start all over again, and re-weld the joint. What you do not want to do is re-weld right over this to fill in the holes, and you do not want to grind it off and re-weld. What you want to do is remove all of the old weld and start all over again from scratch to re-weld that joint. Let's take a look again in the FA figure pages, this time at figure 45. There's a number of different types of welds shown here, and the FA will ask you about them. For instance, they might say to you, which one of these spots on here, A through G, shows a butt weld? Well, a butt weld is shown at point A on here. And with a butt weld, what you do is you put two pieces of material edge to edge, and then you weld them. They're not lapped over each other. They're simply edge to edge, like they are here, and then they're welded. So the butt weld is shown at point A. They might ask you, on the other hand, which area shows a double butt weld? Well, take a look at area B. With a double butt weld, again, the two pieces of material are put together, not overlapping, but side to side, and you have a bead on both sides of the joint, and that's what makes it a double butt weld shown at point B. Or they might say to you, which one of these spots shows a lap weld? Take a look at area G. With a lap weld, you've simply got the two pieces of material overlapping each other, and then you weld the joint. So G is a lap weld. Now let's talk about a fillet weld. A fillet weld is basically simply a T-shaped weld, and the amount of penetration that you need on a fillet weld is